5.1 Extreme values of functions. Let's look at an absolute global extreme values. One of the most useful things we can learn from a function's derivative is whether the function assumes any maximum or minimum values on a given interval, and where these values are located if it does. Once we know how to find a function's extreme values, we will be able to answer such questions as, what is the most effective size for a dose of medicine? And what is the least expensive way to pipe oil from an offshore well to a refinery down the coast? We will see how to answer these questions in section 5.4. We have a definition, absolute extreme value. Let f be a function with domain D, then f of c is absolute maximum value on D if and only if f of x is less than or equal to f of c for all x in D. So in other words, if you have a certain value for c, everything around it is less than that function. That makes it the highest value. Absolute minimum value on D if and only f of x is greater than or equal to f of c for all x in D. So if you have some certain value and all the other values you have are higher than it, that f of c must be the lowest, or it must be the minimum. Absolute or global maximum minimum values are also called absolute extrema. It's plural of the Latin extremum. We often omit the term absolute or global and just say maximum and minimum. Example 1 shows that extreme values can occur at interior points or endpoints of intervals. Let's explore extreme values. On negative pi over 2 to pi over 2, f of x equals cosine of x takes on a maximum value of 1 once and a minimum value of 0 twice. So cosine has a maximum and two minimums, but the minimum value on both just happened to be 0. Sine of x takes on a maximum value of 1 and a minimum value of negative 1. So sine has a minimum value at the left endpoint and a maximum value at the right endpoint. Exploring absolute extrema. The absolute extrema of the following functions on their domains can be seen in figure 4.2. Let's look at y equals x squared, and what if the domain, we were looking at negative infinity to infinity? Then we would have a minimum value of 0 at x equals 0, and there would be no maximum value because these would be going up forever, so no maximums. If we took the same function and looked at just 0 to 2 but include the endpoints, so both would be a solid dot, then we'd have a minimum of 0 at x equals 0, and we'd have a maximum of 4 at x equals 2. If we had an open dot on the left side but a closed on the other side, so open there, closed there, then there would be no minimum value. This keeps going down towards 0 forever, but never actually gets there, so there's no minimum. But there would be a maximum value because it would reach a value of 4 at x equals 2. Then if we have an open interval, 0 to 2, we have an open dot at 0 and an open dot at 2, there would be no extrema at all. There's not a highest value and there's not a lowest value on that graph, on the open interval. If we look at this graph, we have an absolute minimum down here. This is the lowest value. We have a local maximum here, and notice how the slope of the tangent line is 0. We have a local minimum here. Notice the slope of the tangent line is 0. We have an absolute maximum, and the derivative here wouldn't exist. It'd be undefined because we have a cusp here. And then finally we have, on this endpoint, it's just locally a minimum value. Classifying extreme values, local extreme values. If a function f has a local maximum value or a local minimum value at an interior point c of its domain, and if the derivative exists at c, then f prime of c equals 0. This is saying that the derivative at a local minimum or local maximum will be 0. Critical point. A point in the interior of the domain of a function f at which f prime equals 0 or f prime does not exist is a critical point. Points at which the derivative is 0 or the derivative does not exist is called a critical point. You'll hear me say that quite often throughout the course. Finding absolute extrema. Find the absolute maximum and minimum values of f of x equals x to the 2/3 on the interval -2 to 3. We need to find out, well, first of all, we're going to check a value at negative 2 at the left endpoint, and we will check values at the right endpoint. But we want to find out, are there any x values in between that are critical points? In other words, possible mins or maxes. Well, we know that mins and maxes happen where the derivative is either 0 or undefined. So let's take the derivative. That's equal to 2/3 x to the negative 1/3. We have 2 over 3 times the third root of x. Nowhere is the derivative 0. We can't find a value that would make this derivative 0. However, at x equals 0, the derivative is undefined. So that's now a critical point. So we can check f of negative 2, f of 3, and we have to check f of 0. Let's look at negative 2. We need negative 2 to the 2/3. We need 0 to the 2/3. I know that one, it's 0. And we'll need 3 to the 2/3, and we're going to use a calculator to do that. Example 4, finding extreme values. Find the extreme values of f of x equals 1 over square root of 4 minus x squared. Let's start this one by finding the domain of f of x. The denominator can't be 0, and we can't take square root of negative values. So we have 4 minus x squared has to be greater than 0. If we factor this, we get 2 minus x and 2 plus x greater than 0. And this is a parabola with zeros at negative 2 and 2. This parabola goes up to 4, 1, 2, 3, 4, and it looks like this. The parabola is upside down because a is negative. Now we want to know where the values would be positive for this radical, and of course not 0. The domain is negative 2 to 2. That's where these values are positive. Let's find the derivative. F of x is equal to 4 minus x squared to the negative 1/2. So f prime of x, the derivative, is equal to negative 1/2 times 4 minus x squared to the negative 3/2 times negative 2x. That's equal to, well, the 2's cancel out, the negatives become positive, and we have x over, let's see, the square root of 4 minus x squared, and that to the third power. This fraction will be 0 at x equals 0, so that's a critical point. And the possible values that could make the denominator 0, or where the derivative is undefined, is at negative 2 and positive 2, but the original function isn't even graphed at those values. So now we don't even have to consider where this function is undefined because it's not even in the domain. The only place we have to look is at x equals 0. So we look at x equals 0. And then we can plug 1 in, and we can plug negative 1 in. Now we can't plug 2 and negative 2 in to the derivative because it's not defined there. If we plug negative 1 in, we get negative 1 over the square root of 4 minus 1 squared to the third, which is negative 1 over the square root of, it would be 3 to the third, that's 27, but more importantly, this is negative. And then if we plug 1 in, we get 1 over, this becomes the square root of 27, and that is positive. Now if the derivative is negative on the left and positive on the right, this is a minimum of something at x equals 0. Well, if we plug 0 back into the original function, we get 1 over the square root of 4 minus 0, so 1 over the square root of 4. The value is 1/2. So minimum of 1/2 at x equals 0. Now if we look at the graph, here's that point. There's 0, 1/2, and these are open dots, so they are actually not maximums. If they were closed dots, then we would be talking about having some maximum values there. In exercises 1 through 4, find the extreme values and where they occur. Well, these all look like closed dots to me. So we have a maximum of 2 at x equals 0 and a minimum of 0 at x equals plus or minus 2 for this one. In exercises 5 through 10, identify each x value at which any absolute extrema value occurs. Explain how your answer is consistent with the extreme value theorem. We're not going to worry too much about that. We have a minimum, we can only say at B, and a maximum at C. So we have a minimum at one endpoint and the maximum occurred at an interior point. Oh, we have, on this one, we have no maximum. There's an open dot here and the line approaches that value forever. So there's really no maximum value. And on this one, there's no minimum value because the graph keeps going down forever and never actually really reaches that point either. So no min and no max on this one. On number 10, we have a maximum value way up here. So we have a max at A, and we have a minimum value right here down at C. I'm going to have to answer that. Well, stopped ringing. In exercises 11 through 18, use analytical methods to find the extreme values of the function on the interval and where they occur. We're going to have to find g of -1 on this one, and we'll have to find g of +1 on this one, because that's the endpoints. You have to check your endpoints. Let's find the derivative. The derivative of x is e to the negative x times, -1. So that's equal to -1 over e to the negative, actually positive x, if I'm going to put it down in the denominator. Oops. There we go. -1 over e to the x. Now, there's no way to make the denominator 0. E to the x cannot be 0. So there are no critical points for this function. So if we plug in g of -1, that's e to the -1, that's e. And if we plug in a +1, that's e to the -1, that's equal to 1 over e, which is a fraction. It's less than 1. So we have a maximum of e at x equals -1 and a minimum of 1 over e at x equals, where's that one? At +1. Example 18, f of x equals x to the 3/5 from -2 to 3. We'll have to look at f of 3 because it's an endpoint that we're going to include. It is the closed side, and we don't have to look at the open side because the function will approach -2 forever but not actually get there. Our next step is to find the derivative and look at where the derivative is either 0 or undefined. So the derivative is 3/5 x to the -2/5. That's equal to 3 over 5 times the 5th root of x squared. You can't make this fraction 0 because the numerator is a 3, but we can find a point where this is undefined. And this is undefined at 0. Now if I plug 0 into the original function, I of course get 0. But we need to decide if that is actually a maximum or a minimum. Now if we throw this on a number line, 0, and we plug in, let's say, -1 and +1, we need to see that the derivative, or the velocity, is going to the right and then going back to the left in order for this to be a minimum or maximum, or vice versa, go to the right or go to the left and then back to the right. So if I plug -1 into the velocity, or the derivative, we get a +3/5 because you're going to square -1. That'll be positive. 5th root of 1 is 1. So that's a positive. So this is moving to the right. Then we find out where the velocity is undefined. And then this thing keeps moving to the right because if you plug in 1, you get another 3/5. Now, in order to be a minimum or maximum, the derivative has to change signs. And even though there is a point at 0, the derivative doesn't change signs there, so it's not a minimum or a maximum. Let's look at 3. And we got plug 3 in. 3 to the 3/5. Let's grab our calculator and do that. We have, let's clear that, 3 raised to the 3/5. value is 1.933. 1.933. Well, other places to the left of 3, the value is 0, but we said that's not a min or a maximum. And then the function is increasing to 1.933. So we have a maximum of 1.933 at x equals 3. Find the extreme values of the function and where they occur. And this is not on an interval. This is everywhere, negative infinity to infinity. Let's find dy dx. That's equal to 3x squared minus 2. And we set the derivative equal to 0. So we add 2, divide by 3. So x equals plus or minus the square root of 2/3. Let's put those values on a number line. These are the critical values. So we have negative square root of 2/3. We have 0 is in between the positive square root of 2/3. And this is a fraction. 2/3 is a fraction. It's less than 1. And when you square root, it'll be even more less than 1. So we're pretty safe to check 1 and negative 1. If I plug negative 1 into the derivative, we get 3 times negative 1 squared. That's 3 minus 2. That's positive. If I plug 0 into the derivative, that's negative. If I plug 1 in, it is positive. So this function is increasing, decreasing, and then increasing. So if your function increases and then decreases, so increases then decreases across that value, increases then decreases, you have a local maximum. So we have a local max of something at x equals negative square root of 2/3. Let's look at the instruction. It says find the extreme values of the function where they occur. So we have to plug negative square root of 2/3 in. And we also have a local minimum of blank at x equals positive square root of 2/3. So now we got to find those y values. We have x to the third minus 2x plus 4. And I want to find f of, well, this is f of x. We want to evaluate this at x equals negative square root of 2/3, which is negative square root of 2/3 to the third minus 2 times negative square root of 2/3, and then plus 4. So that is, let's see, we would have negative 2/3 times the square root of 2/3 plus 2 times the square root of 2/3 plus 4. So this value is, see, 2/3 and 6/3 is 4/3. So 4/3 square root of 2/3 plus 4. Wow, what a number. 4/3 square root of 2/3 plus 4. And then if I plug the positive in, we get square root of 2/3 to the third minus 2 times square root of 2/3 and then plus 4. We get 2/3 square root of 2/3 minus 2 square root of 2/3 plus 4. So we have 2/3 minus 6/3 is negative 4/3 square root of 2/3 plus 4. Number 24, y equals 1 over x squared minus 1. Let's start this one by looking at the domain. And x squared minus 1 cannot equal 0 because, well, we can't allow the denominator to be 0. We have x squared cannot equal 1, and so x cannot equal plus or minus 1. So the domain is everything except 1 and negative 1. Let's write the function as x squared minus 1 to the negative 1, and we'll just use the power rule to find the derivative. We have y prime now is equal to negative x squared minus 1 to the negative 2 times 2x. That's equal to negative 2x over x squared minus 1 squared. Now, the critical values are where the derivative is either 0 or undefined. Well, the derivative is 0 at x equals 0 and undefined at plus or minus 1, but we discovered that plus or minus 1 is not even in the domain, so we really don't have to look at those values if they're not in the domain. Let's look at 0. We have 0. And we would have negative 1 and 1. That should be 1 on the right side. And negative 1 over here. But those aren't in the domain. So we better check negative 1/2 and 1/2. Now when we plug those values into the derivative, we get negative times negative 1/2 as a positive. And then the denominator has to be positive because we're squaring it. So negative times a negative is a positive. And then across 0, the derivative goes from positive to negative. This is a maximum value. If your function has positive slopes and then changes to negative slopes, positive slopes, then negative slopes, we have a maximum value up here. We have a maximum of, let's plug 0 into the original. If we plug 0 in the original, we get negative 1. So maximum of negative 1 at x equals 0.